Welcome to this explainer. Today, we're diving into a literal game changer in agricultural tech. We're talking about a massive paradigm shift that was basically born out of sheer necessity. We are finally ditching the ancient, failing practice of surface irrigation, and we're heading straight into the high-tech, subterranean world of robotic swarms. This technology is completely rewriting the rules of how we grow our food and, honestly, how we secure our future on a rapidly warming planet.
All right, here's our roadmap for today. We'll start with the 2026 evaporation crisis, look at the evaporation trap, and then dive into the rise of robotic swarms. After that, we'll cover AI-driven root hydration, hemp as the ultimate carbon sink, and finally, greening the dust bowls. Let's get right to it. Starting off with Section 1, the 2026 evaporation crisis, and exactly why traditional irrigation is totally failing our climate.
Here's a staggering number to keep in mind: 60%. Under extreme heat, up to 60% of the water we pump through traditional surface irrigation, your standard sprinklers or flooded furrows, is just utterly wasted. Think about that for a second. More than half of this desperately needed water vanishes before it even touches a single active root. When the top few centimeters of soil hit 60 degrees Celsius, they literally bake into this hydrophobic, waxy barrier. So we haven't just hit a water shortage, we've hit a catastrophic delivery crisis right at the surface, and it directly threatens our food supply.
Which brings us to Section 2, the evaporation trap. Let's break down the actual physics of this topsoil water loss.
The difference between these two methods is honestly night and day. With the old paradigm, surface irrigation, we're basically trying to fight physics. We dump water onto a scorchingly hot surface, fight massive thermal barriers, suffer huge capillary loss, and end up creating these toxic salt crusts when the water boils off. But the new paradigm, the subsurface bypass. This approach completely ignores the surface. By delivering water directly underground, we eliminate surface evaporation entirely and actually preserve the soil structure. Instead of fighting the intense heat, we just bypass the whole thing.
Because here is what's happening. The topsoil essentially acts like a giant radiator. First, you have this capillary siphon pulling moisture upward, literally acting like a wick in an oil lamp. Then, the thermal barrier at the surface hits that 60-degree mark and vaporizes the water instantly. The moment it gets there, poof, it's gone. And finally, this rapid flash drying causes a crust effect, a rock-hard, salty shell that blocks any future water from soaking in. It is a vicious cycle, leaving crops totally parched, regardless of how much water we throw at them. So how do we fix it? Section 3. The rise of robotic swarms, or as I like to call it, microsurgery for the soil. The absolutely crucial point here is targeting what's called the rhizosphere. This is that exact tiny underground microzone immediately surrounding the plant roots, where all the complex chemistry of nutrient and water exchange actually happens. The goal isn't just to broadly soak a whole field. The goal is pinpointing this rhizosphere. If we can hydrate just this tiny, specific area where the plant absorbs its lifeblood, we don't need to waste thousands of gallons soaking empty dirt.
And in practice, this honestly sounds like straight-up sci-fi happening right under our feet. We aren't talking about static, leaky pipes. We're talking about autonomous 40-centimeter titanium polymer capsules. First, they navigate through the dirt, well, actually, dirt's the wrong word, through the delicate soil ecosystem, using these tiny microdrives, completely avoiding damage to roots or vital fungal networks. Then, they use an ultrasonic phased array pinging out between 40 and 100 kilohertz to map out a 3D moisture gradient of the soil in real time. Finally, instead of flooding the zone, a mechanical injector fires a hyper-precise microdose, just 0.1 to 2 milliliters of water at 5 meters per second, right into the root zone. This prevents waterlogging and keeps the soil perfectly oxygenated.
Moving on to Section 4, AI-driven root hydration and the Cortex Agro ecosystem.
Now this is the brain behind all that robotic brawn. The Cortex Agro Central AI coordinates massive swarms of over 100,000 probes at once. It pulls in telemetry data from every single node every 10 seconds, monitoring moisture, temp, root activity, and uses all that to build a complete digital twin of the entire field. It doesn't water uniformly, right? It creates a fully dynamic, localized moisture grid. That means every single individual plant gets its own custom hydration schedule. By completely eliminating plant stress and neutralizing that vicious evaporation trap, the energy the plant would normally spend just trying to survive a drought is poured directly into explosive growth.
Which sets us up perfectly for Section 5, hemp, the carbon sink and its explosive exponential growth.
When you pair the massive tap roots of industrial hemp with this robotic swarm's perfect, stress-free hydration, the results are unprecedented.
When comparing the numbers against historical traditional surface irrigation, the dry biomass yield of hemp just explodes by up to 3.2 times. And incredibly, at the exact same time, water consumption plummets by 85%. Because the plant never goes through that brutal drought then flood shock, its photosynthetic engine is basically running at absolute maximum efficiency all the time.
And here is the so what, the jaw-dropping planetary impact. A single hectare of this precisely irrigated hemp can capture up to 25 tons of carbon dioxide in a single season. To put that into perspective, that is double the carbon capture rate of a typical temperate forest. Double! These deep roots push stable organic carbon way down deep into the soil profile, creating this massive long-term reservoir. So we really aren't just talking about farming anymore. This is planetary engineering. It gives us a genuinely faster path to stabilizing our climate and protecting communities from increasingly erratic weather.
And finally, Section 6, greening the dust bowls. Let's look at the broader economic and planetary impacts here.
The economic argument for this technology is crystal clear. Now, yeah, there is a hefty upfront capital cost. It's roughly $2,000 per hectare for the robotic probes. But the returns, they're unbelievable. Water loss plummets from up to 70% down to under 2%. Energy use drops to just a quarter of traditional methods, mainly because shooting a tiny microdose takes way less pump pressure than running massive industrial sprinklers. Plus, as we saw, yields skyrocket by 300%. The grand result of all this is that the entire system completely pays for itself in just 14 to 18 months. Honestly, in regions where water is literally becoming more expensive than energy, this kind of precision is the absolute only profitable path forward.
And the craziest part? This isn't some distant pipe dream. The rollout is already happening. Between 2026 and 2028, we're already seeing massive pilot deployments in severely drought-stricken areas like California and the Colorado River Basin. Building on that momentum, from 2029 to 2031, this infrastructure will rapidly expand across the Sahel in Africa and Central Asia. By 2032 and beyond, we're genuinely looking at the global standardized replacement of surface irrigation. It's going to fundamentally change how the entire world grows its food.
So I want to leave you all with a profound question, one that really dictates human survival and the future of our ecosystems. As the sources put it so brilliantly, we didn't conquer the drought, we just learned to go where it isn't, underground. So are we going to stubbornly keep evaporating our most precious resource into the blazing sky? Or will we finally embrace the tech and master the world beneath our feet? Thanks so much for tuning into this explainer. Keep asking those big questions, and I'll catch you in the next one.